Welcome back. So let's continue with this example that we were looking at in the last lecture, where we got this particular solution 42800, and then we wrote the general solution in this form, right? But what I'm doing here is simply just taking those values and checking whether they are fitting into the equation. Okay, so let me pull the equation back for a second, and then we can check how I got to write these equations, right? So I'm just going to take this a little bit, so fold this a little bit. So as you can see here, we got this equation. We started with 108 minus 4, x1, x2, x3, x4, 0, 1, 2, 12, x1, x2, x3, x4, and then this first equation is exactly this, right? So I've just taken this equation x1, and then this second one is 0, so that's gone, and then 8x3 minus 4x4 equals 42, and then x2 plus 2x3 plus 12x4 equal to 8, right? So those are the two equations. So what I have done here is simply taken these, and instead of lambda 1 I am using a, because it's easier for me to write, and instead of lambda 2 I am using b. Okay, and I have written x1 equal to, the top element is 42 plus 8a minus 4b, and x2 is 8 plus 2a plus 12b, and x3 is, this is 0, this is 0, so only this one, so that's negative a, and x4 is, these two are 0 and negative b. Okay, so I'm just checking whether these values work in this equation, right? So that's all I've done here. So I've just taken 42 plus 8a minus 4b for x1, which is this guy, plus 8x3, which is minus 8a, and minus 4 times minus b, and that you can see all these terms cancel out and becomes my 42. And then this one is x2 plus so x2 is 8 plus 2a plus 12b, 2 times x3 minus 2a, and then plus 12 times negative b, which is minus 12b. So you can see that this 2a and 2a cancel, and 12b and this 12b, they cancel each other, and we are remaining thing is 8, and that's what it is, right? So this is a way that you generally can verify whether your answer is correct or not. Okay, so next we will proceed with Gaussian elimination based on elementary transformations. Okay, so what are these elementary transformations? So if you remember from school days, like two equations in two unknowns, we'll multiply one equation by a constant and then try to subtract or add the two, eliminate one variable, and then solve for x and y, right? So if you remember from school days, that's what we used to do, and then maybe you have some experience even solving a three equations in three unknowns case, right? Now we can do that in general for n variables and m equations, right, which is what we are doing here. So they are called elementary transformations, which means you change your system of linear equations to a simpler form which is easier to solve. Okay, and what are the steps that are useful, or the transformations that are useful for transforming something like this, which is the original set of equations, into a form which is more suitable for easily solving for the variables. Okay, so what are the steps? Exchange of two equations, which is same as rows, because each row is an equation. Okay, so exchanging two equations means you move things around, right? That doesn't really change anything, so that works. Multiplication of an equation with any non-zero real number, right, or a scalar. In this case, as you can see, lambda belongs to the set of real numbers but 0. Okay, so that's this notation, if you remember from the notations discussion that we had, right? So we take any non-zero real number and we multiply the any equation, it works because it's an equality, so you can multiply both sides by a constant, so that works. Okay, then the last one is addition of two equations. Obviously, if this equation is true and this is true and we want to solve for this, if you add them up, or if you even subtract, really, right? But generally only addition is specified because subtraction is same as multiplying one of the equations with a negative number and then adding, right? And since this lambda is any real number, it can be negative. Okay, so that's why that works. So they have given this example 2.6 in the book. The reason that I have written all this ahead of time is because actually I did record this live, but for whatever reason the recording did not come out very well. I maybe ran out of space on my mobile phone, and then I realized it's quite tedious to sit and see me write all these things. So it's easier if I had these equations already written, then I can easily explain what's going on, right? So in a way it became a blessing in disguise for you, I guess. Okay, so this is example 2.6. There are 4 equations and 5 unknowns, right? x1 to x5, and these are the 4 equations, and this a is some real number. Okay, and what we can do is take this system of linear equations and write it into this augmented matrix form, where we only take the coefficients and write it down here. So if you see this -2 is the coefficient of x1, and then the 4 -2, and this is -1 that comes here, 4, and then the right hand side, this one we just put this vertical line and then write them down here, -3. And similarly we have done for the other 3 equations, and we got this matrix which is known as augmented matrix. Let me ignore this let's ignore that for a minute. The reason for this augmented matrix notation is we don't need to unnecessarily carry these x1, x2 and all throughout our elementary transformation, right? But it's equivalent, so it's easy to just deal with the numbers. Okay, now looking at this, what we are trying to accomplish, if you remember from the previous example, let me pull that out. We had this nice form, if you remember, in the matrix, this identity matrix sitting here, right? This kind of form is useful and helps us solve this equation more easily. So we want to get a 1 at the top here through elementary transformations so you can do any of these sequence of elementary transformations and then somehow get a 1 here and then strive to get zeros below it, right? So we get kind of that identity matrix kind of form. That's the general idea, right? And what we do in this case, we can take this first row and multiply it by -12. If we do that, we get a 1 here, right? And that's one way to do it. The other way to do it is you can swap or exchange of 2 equations, right? So I can take the third row, put it here, and take the first row and put it here, which is what I am denoting by this R1, R3 getting swapped. Okay, so when we swap those two, so we end up with this equation, right? Sorry, this augmented matrix now, right? Where all I have done is, let me see if I can just pull the previous page down and then continue this, because this is running several pages, right? I don't think that came out all right. Let me just push it down a little bit more. Oops. Okay, let me make sure this guy is stable. Okay, so what we have done is very simple, right? So we've taken row 1, put it here, right? You can see the row 1 here has become row 3 here, and the row 3 here has become row 1 here. All right, and that's it, right? Nothing else we are doing. So first step is good. We got a 1 in the top left corner. In the top left element has become 1, and that's excellent, right? Now once we got this, what we want to do is we want to eliminate all these non-zero values and make them 0. And how do we do that? So for a moment, let's ignore all this. So I have 4 here. So if I multiply this by 4 and subtract, I get a 0, right? That's what I've done here. So R2 has become R2 minus 4 times R1. R3 has become R3 plus 2 times R1, because I just need to take 2 here. So if I multiply by 2 and add it to this becomes 0. Then R4 minus R1 is going to again give me 0. And that's exactly what I have done here. So let's just go through the math here, right? For at least one of them. So let's take R2, right? So R2, 4 I have, multiply this by 4. So 4 minus 4 becomes 0. Then minus 8. Then this is minus 4 times minus 2. So that's plus 8. So you sum them up, that becomes 0 also, right? This is kind of not always the case, but in this case, it just happens to become 0. Okay. This one, 3 minus 4 times 1. So that becomes minus 1. And then this is -3 minus 4 times -1. So that becomes -3 plus 4. So that's 1. Okay. and then this is 1 minus 4, that's minus 3, and then 2 minus 0 is 2, and we do this 2 times r1, we add that, and then we get this row, and then we just subtract r1, we get this row, right, the last one, right? Now in the book they are doing little bit different steps, but this one I hope is clear. Okay, so this is what I have done. The next step that I am doing is, you see that from the left hand side, when we look at the non-zero entry, the first top row should have a 1 here. That's kind of the idea. The second row, anything 0 is okay, but then we want to make sure this guy is a 1, right? Just like this guy became 1. So we are trying again to push this towards identity matrix. Okay, so we multiply just simply the second row by minus 1. So the only thing that changed here is just the sign of the second row, right? That's it. And then now we got a 1 here, so this is good. Now I should make this 0 because I don't want this non-zero entry here below this 1, right? So I have done r4 as r4 plus r2. So you carry out the math where this r4, now we are replacing with this r4 plus this guy, right? So 1 minus 1, that becomes 0, minus 1 minus 2 is minus 3, 3 is 6, and then this becomes a minus 2, everything else remaining the same, right? Now what is the next step? Now this column is taken care of, everything below is 0. Now we come here, right? This, as you remember, from the left hand side I'm looking 0 0 0. Now this I have to make 1, so natural thing, multiply by minus 1 by 3, right? So then this becomes 1 minus 2 and 1, right? So that's all I have done here, 1 minus 2 and 1. Okay, so let's move on to the next page. Okay, so other than that third row, everything else remains same. Now this last row has a minus 3, so we have to make this 0. So multiply this times 3 and add it. So we get r4 as r4 plus 3 times r3. So minus 3 plus 3, that becomes 0. 6, okay, this also becomes 0, which is not always the case. In this case this becomes 0 also, because 3 times minus 2 minus 6, so you add them up, and then a minus 2 plus 3, that becomes a plus 1. Okay, now nothing else to do, okay, because we got 1 and then all zeros. This guy is fine because it has all zeros, and then this one has a 1 and this one has a 1, and this is all 0, right? No problem. Okay, this form is called row echelon form, REF. Okay, and this is kind of useful because we have simplified the equation now to this. I'm just writing this now, basically what this augmented matrix means is these equations, correct? We did the inverse where we initially started with equations and then we wrote the augmented matrix in the previous pages, right? So like this, we did this, right? We started with the equations, we wrote the augmented matrix. Here we are just doing the reverse. We are taking this augmented matrix. This is just x1 minus 2x2 plus x3 minus x4 plus x5 equals 0, and these equations also come. Only interesting thing is the last one, there is no variable, it just says a plus 1 is 0. So the system of linear equations can be solved only for a equal to minus 1, right? Because a plus 1 has to be 0, so a has to be minus 1. That's the only case for which we can solve this system of linear equations. Now so far so good. Now if you follow the book, they are writing this particular solution for this system of linear equations where if you follow the example, which is example 2.6 in the book, they have given this particular solution in the example itself, which is a little bit surprising because it doesn't, it's not immediately obvious how they got it, right? So couple of more steps need to be done to this row echelon form before we can write this particular solution, right? So what the idea is, okay, we got 1 here and 0 0, row echelon form is nice, but I don't want this one also, because I want this one to be the only non-zero element in this column, right? Then it's more closer to identity matrix, right? And then here also the same thing, right? I want only this one and I want to make these 0, right? So let's carry out some more elementary transformations. So this augmented matrix becomes even simpler. Okay, so let me just go through those steps. So here what I have done is, so let me go through this. Okay, so I'm just going to, so maybe a little confusing, so let me keep this a little bit aside so you can see. So this 1 minus 2 1 minus 1 1 0, that one went to the first row as it is, no problem. The second row went here, the third row went here. Now the fourth row we don't need because it's all just zeros. It's not going to help us solve anything. We just know that a equal to -1. Okay, so we'll leave that aside right now. So we take only these three rows. Okay, very simple, right? So the first three rows of this matrix are taken and written there. That's it, nothing fancy there. Okay, now what do we do with this? Now I don't want this 1, I want to make it 0. Then simply I just subtract r1 minus r2, and then this becomes 0, and rest of it, whatever the math, is fine, right? But these two don't get unaffected, because no matter what you do, this is just going to remain 0, right? So that's the beauty, right? So now this became 0, so I got 0 1 0. And then for r2 I want only this one, right? Because now we're done with this row as well as this column. Now we go here, we don't want this -1, so we want to subtract, so we just add r3 to this, then that also goes away. Now we write the equation here. It's x1 minus 2x2, and then this is minus 2x5 equals 2, and then these two guys are gone. X3 plus x5 is -1, and then x4 minus 2x5 equal to 1, right? Now what this means is, wherever there is a 1, those corresponding variables, for a moment we'll leave them aside. The other guys, right, like x2 and x5, we did not. So for example, the variable corresponding to this one is x1, this is x2, but then it is kind of, this is a free variable. We'll know what a free variable is, we'll discuss that in a minute, but you don't have a 1 here. So this x2 is kind of like, we can set it to something, okay? And then this x5 is also similarly something. As you can see here, this x5 appears all over the place, and it's a free variable, so the easiest thing is obviously set x5 equal to 0. The moment you set x5 equal to 0, right, we are looking for a particular solution right now that the book has given, right? So we set x5 equal to 0, then automatically this equation implies x3 equal to -1, and this equation implies x4 equal to 1, right? So that's good. Then we come to this equation. In this equation, x5 already is 0, so this is gone. Now we set x2 equal to 0, then we get x1 equal to 2. Now this is the particular solution they have gotten in the book. I have just written this column vector as a row vector. When you write row vector, you put commas, and then you put a transpose. Now this is the same particular solution that they have given in the book. This is the exact same thing, just the transpose of this, right? And obviously this is not the only particular solution that you can get. For example, let's say you don't choose x2 to be 0, but if let's say you want to give x2 equal to 1, right? If you can also choose x2 equal to 1, right? And then in that case x1 becomes 4. That becomes the particular solution, right? So the particular solution is obviously not unique. It's just a convenient and easy solution that you can quickly come up with once you have it in this much nicer form, which we will discuss more in the next video. Okay, hopefully that helps. Maybe this video it went a little bit faster than the others since I had written down everything already, but hopefully the steps were clear, and you can maybe go with the video a little bit slower and work out the math yourself and do all these steps by yourself and see whether you get these results. Okay, I'll see you in the next video. Thank you for watching.